All right, we're still in chapter 4, studying motion, but now we're specifically going to talk about free fall. We drop an object and we can see by the spacing that it is increasing speed. You might recall we did a lab on this. We dropped the ball about 1 meter, slow motion video. We watched it, got the times, plotted the position versus time, drew a best fit curve, found the slopes of some tangent lines, graphed the velocities versus time, saw it was a linear relationship, and found that slope, which was the acceleration. The class data worked out to be about 10 meters per second squared, and the right answer is 9.8 meters per second squared. That's the acceleration due to gravity. And since this is a straight line, we realized that gravity was a constant acceleration. Well, somebody asked, what if we had a larger ball? Would they both still fall at 9.8 meters per second squared? Well, we had a discussion about that. The larger object would have a greater force. The idea was that if it weighs more, it should fall faster. Hey, if you push on something harder, it'll move quicker. But what else do we have to consider? How about the mass of the object? If you have a ball that weighs more, it's going to have more mass. More mass makes it harder to move. The way gravity works is if you have something that weighs twice as much, it has twice as much mass. Seemed like all the kids had heard about inertia. That's the mass, a resistance to a change in motion. It's harder to move something that's twice as massive, but you have twice the force. So it cancels out and they all fall at the same rate. More on that in an upcoming chapter. So let's take a look at a problem. We're going to drop a ball from a height of 100 meters and have it land on the ground. We're going to assume that down is negative, up is positive. How long will it take to fall? We could just say that the distance is equal to 1/2 AT squared plus VIT. We're going to break this up into y final minus y initial, and I'm going to make that negative 9.8. I said we're going to make down negative. That's up to you. You can make down positive if you want to, but I'm doing this example with down being negative. What's my initial velocity? It's 0, so that term goes away. If I set it up this way, I have final height of 0 and initial height of 100 meters. Look what happens to the negative signs. They cancel, and we get a positive 4.52 seconds. Those negative signs canceled. It wouldn't have mattered if we called this down positive or negative. You'd still get the same time then. Could we find the final velocity when it hits the ground? Let's use the acceleration equation. A little algebra, and this is what we have. The v initial is 0. So we have a final velocity of 44.3 meters per second, but that's a negative sign, so we should make that negative. We said down is negative. Let's make a graph of the height versus time, y versus t. Now remember, don't go drawing the whole graph. Just try to draw one point to start with. We started 100 meters, so we'll put a dot high up. If we release the ball from rest, the initial velocity is 0, so that slope should be 0. So in a little while, we fall, and then in the same amount of time, we fall further. And in the same amount of time, we fall further again. This is agreed upon by the diagram over here. And it's a parabola, borne out by the fact that the distance is equal to 1/2 AT squared. To do the velocity versus time, we have to ask ourselves, what is the initial velocity? Start with the first point. 0 velocity. Now look at that slope. It's negative. So we have a negative velocity. The next slope, even more negative. The last slope, more negative yet. Sure, it's a linear relationship. And the acceleration versus time, negative 9.8 meters per second squared the whole way. And these graphs agree with the formulas. Parabola, yeah, it's 1/2 AT squared. Velocity, it's a linear function. Acceleration is constant. Next problem. Let's say I throw a ball up into the air at 30 meters per second. How long would it take to get to the top? What would be this maximum height? The acceleration formula can help us with the time up. If we say down is negative, then this has to go in as a negative 9.8. The final velocity, which is not explicitly said here, but we know it's got to be 0, because when we get to the top, can't go any higher, the velocity is 0, just for that moment. And then we have a minus v initial. Well, that initial velocity is a positive 30 meters per second. If this is going up and that's going down, they both can't go into the equation as negative. They both can't go into the equation as positive. One has to be negative, the other has to be positive. Rearranging, we get 3.06 seconds. This is actually useful when you talk about getting to the top of the trajectory. This would be called time up. And you might notice that the negative signs are going to cancel. So we can make a formula now and just say time up equals v initial over g. And we put in g as a positive 9.8. Now we have to get h max. We'll use the distance equation. Notice we're putting in a negative 9.8 and a positive 30. They both can't be in the same direction. Looks like we went up 45.9 meters. So here we have our two answers. Now let me point out that the maximum height is also the distance the ball would fall back to the ground. That actually has an advantage. If we drop to the ground, the initial velocity is 0. I don't need the VIT. I don't even care if I call that negative or not. There's nothing else to contradict it, so it's just going to go down. So now this tells me I fell 45.9 meters. Hey, that's the same as the maximum height. That looks a little easier to do. Even easier. How about the V average? Hey, if that's 30 and that's 0, the V average is 15 meters per second. Don't even need a calculator for that. V average times time, that's how far you're going to go. Yeah, 45.9 meters. Many ways of solving the same problem, and if they all agree, we probably know what we're talking about. Time for the graphs. Why don't you pause the video and try doing it yourself first? All right, the first thing we want to do is figure out where we're starting. First point, at time 0, we're on the ground. A little while later, we're higher up. And a little while later, we're higher up, but we didn't travel quite as far because we're slowing down. In the next time interval, we don't travel as far either, so we're eventually going to reach the top. And you can see how this curves. And we'll see the same thing on the way down. Let's take a look at these slopes. High slope means we had an initial velocity that was large. At the top, the slope was 0 because the velocity was 0. On our way down, just as we hit the ground, we're going fast in a negative direction. So we have our initial velocity, the velocity at the top, and the final velocity. If we go to make a graph of velocity versus time, we start with a high velocity. At the top, we're at 0 velocity. We get back to the ground, we have a negative velocity. It's a straight line all the way through this. The slope of that line is the acceleration. What's that look like? Horizontal straight line, but negative. Negative 9.8. Now I'm going to ask you a question about this graph. What's the acceleration of the object when it gets to the top? Well, the velocity is 0, and a lot of kids will tell you, oh, that means the acceleration is 0. That's not true. When you get to the top, that doesn't mean gravity has stopped. It's still pulling down. You have a negative slope the whole way. So it's not that it's the 0 velocity that tells you anything about the acceleration. It's the change in velocity. Change in velocity, change in time. Change in velocity, change in time. Change in velocity, change in time. It's all the same slope all the way through. So what's the acceleration when the ball gets to the top? Negative 9.8. Let's just prove this with the formula as well. What do we have on the way up? Well, the final velocity is 0. The initial velocity is a positive 30. It's going to give me a negative 9.8 meters per second squared. What if we use the formula on the way down? The final velocity on the way down is going to be a negative 30 when it hits the ground, starting at 0 at the top. So it's final minus initial divided by that time. We still end up with a negative 9.8. So it doesn't matter whether you're going up or going down, the acceleration is still a negative 9.8. Sometimes it's useful to estimate the time up just to see if we've got a reasonable answer. Maybe we made a mistake with the calculator. You could do this in your head. Just round that off to negative 10. Take a look at this. You're going 30. In 1 second, you'll be going 20 because we're losing 10 meters per second every second. So we're going 30 meters per second, 20 meters per second, 10 meters per second, and then 0. How long will it take us to go up? Approximately 3 seconds. So it's not a bad idea to keep those estimations in mind. Now let's talk a little bit about air resistance. I told everybody that you had a little square of paper, 1 centimeter by 1 centimeter, and a quarter, and let them drop to the ground. Who's going to win? Well, obviously the quarter's going to win. How come? Everybody says that there's air resistance on the paper. But isn't there going to be air resistance on a quarter as well? Sure there will be. But there's going to be another force acting on both of these objects. There's the weight of the paper and the weight of the quarter. Now you know that quarter weighs a lot more than that paper. So which do you think the air resistance will affect more? Yeah, it's going to be the paper. There's not that much weight to the paper, so the air resistance is more significant. In this situation, that weight of the quarter is just going to let this quarter plow through the air. You won't have as much of an effect of the air resistance. Then I told you to put the paper on top of the quarter and let go. Hey, if you're careful and you hold that quarter flat when you release it, they both get to the bottom at the same time. Okay, so what happened? The quarter blocked the air. So the paper was able to fall due to gravity without that effect of air resistance. So if we did this experiment in a vacuum, or we do it on the moon, you're going to get the same results. We'll see that later. Putting the paper behind the quarter reminds me of something called drafting. The track runners know that. If you're running cross country and you've got a strong, stiff headwind, they tell you to stay behind the other runners so it's easier for you. They block the wind. Same thing in cycling, or the same thing in car racing. You get behind another car, you're going to have that car block the wind. Much easier for you to move forward when you can block the air resistance. Let's get a little mathematical. You're driving down the road and you stick your hand out the window. Yeah, that's a pretty big hand. And you're holding your hand such that it's facing into the wind. You feel that force of friction. What happens to that force of friction if you go faster? It gets bigger. In fact, it goes up by the velocity squared. There's experiments to prove this. But I'm sure you've noticed it. If you were parked, you don't feel any air resistance. You start to go faster and you'll definitely feel it. Now, what if you held your hand flat going into the air? It's going to change the amount of air resistance. This is what we call the cross-sectional area. If this block was pushing through the air, it would be a lot easier if we laid it flat. We'd have less area that we're pushing through. Now, why does this car have a pointed end to it? Why don't they make cars with a flat front? Well, obviously, this is more aerodynamic. It's more efficient to direct the air over the smooth curve than to run into a wall. The shape is described by what's called the coefficient of drag. The more aerodynamic, the lower this number. So a nose cone for a rocket might be like 0.2 or 0.3. A flat wall might be 1. If you read about car reviews on certain magazines like Car and Driver, they'll tell you about the coefficient of drag for that model of the car. The Tesla Model S has a very low coefficient of drag. Now imagine you're trying to push your hand through air or water. Would that make a difference? Of course it would. If you push your hand through water, you're pushing a lot more material out of the way. And that's based on the density of the material. or the medium. If you go up to a high mountain and you try to go through the air, there's less air. It's less dense, less friction. This also makes a difference in sporting events. A baseball will travel further in lower air resistance at a higher altitude. The mathematical derivation for how the air bounces off the object gives rise to a 1/2 here as well. Well, we're not doing a serious derivation of this formula. We're going to collect all of these terms and just call it B. The drag force is proportional to the velocity squared. All of this is going to be a constant. If you're driving in your car, the coefficient of drag, the cross-sectional area, and the density of the air will not change, but the velocity will. So we're going to take these and just use it as the letter B, and then here we have our formula. This seems to model objects that are moving relatively fast, like a baseball or a car driving down the highway. For objects moving slower, this is a better model. The exponent is a 1. V is a different constant. It's not the same. The units won't work out. This model works better for things like a soap bubble drifting to the ground in the air. We're going to drop an object from rest. What are the forces acting on it? You've got gravity. And a lot of kids are quick to jump and say, well, now you're going to have air resistance. But don't forget the velocity is 0. If that velocity is 0, force of friction is 0. Well, after a little while, that ball is falling, and we now have a velocity. What are the forces in this situation? The weight's still the same, and now we have some friction. That's the air resistance. Well, later on, that velocity is going to get even bigger. The weight is still the same, but what's happening to my air resistance? If that velocity is bigger, the air resistance is bigger. Now, how big could that air resistance get? At some point, it's going to go fast enough so that this friction will equal the weight. Something special is going to happen. My acceleration is going to be 0. The weight is canceled by the force of friction, and there's no net force. That doesn't mean that we've stopped. It means that the velocity can't get any bigger. And we give a name to that. We call it terminal velocity. And we can put a subscript T right there. Let's go back. What's the acceleration here then? It's going to be negative 9.8 meters per second squared. There's nothing holding us back. It's all gravity pulling down. And what about when we get here? There is some friction holding us back, so the net force is smaller. The acceleration won't be as big. Maybe negative 7 meters per second squared. And then eventually, as the friction gets big enough, because the velocity got bigger, we're going to have 0 acceleration, and we'll reach terminal velocity. Back to the graphs. We're going to drop the ball from rest, but from a very high height. What's that graph look like without air resistance? I think we all know that is the answer. But what will it look like if we had air resistance? Pause the video and try it yourself first. We're going to start at the same height. We have the same initial slope because we're dropping it from rest. But the graph is going to start to get elongated in this direction. It's going to take longer for it to drop the same height. That trend continues. We'll talk more about that in a moment. What about the velocity versus time? Without air resistance, it's that diagonal starting from 0 velocity. That slope is negative 9.8 the whole way. But what about with air resistance? You don't notice much difference at first because the ball doesn't go very fast. It takes velocity to get that friction going. But once you do, that slope is going to start to level off. As the air resistance builds up, that slope will go to 0. You won't be speeding up anymore. You've reached terminal velocity. Now, what does that have to do with this graph here? If this velocity starts to level off, that slope has to become straight, constant, terminal velocity. And of course, the acceleration, negative 9.8 if there's no friction. And keep in mind now, when the ball starts to fall, it has 0 velocity, so it won't have any friction either. When we include air resistance, it'll still start to fall at negative 9.8. And as time goes on, the friction builds up and the acceleration starts to approach zero. This is very tricky. This is a curve, and you'd never be able to figure that out unless you either did some complicated math or a little computer simulation, which we will see later. The important thing to know is that the acceleration goes from negative 9.8 and it gets closer and closer to zero as we reach terminal velocity. All right, let's wrap this up with a problem. A 3-Newton ball falls in air. B is 0.08. What are the units for B? Now, if we assume this ball falls fast enough, we'll say the drag is equal to BV squared. That's going to be the case unless I tell you otherwise. For example, if I said it was, say, like a soap bubble drifting slowly to the ground. What are the units for B? Let's look at the other units. Newtons for force. Meters squared over seconds squared for velocity squared. That means B has to have a Newton in it. And then we have to cancel out the meters squared over seconds squared with a seconds squared over meters squared. That would be the units for B. Now we'll find the terminal velocity. Let's draw a free body diagram. What are the forces acting on the ball when we reach terminal velocity? You have the weight and the force of friction. And they've got to be equal to each other because we're no longer speeding up. So if I use the force of friction equals BV squared, the force of friction has to be equal to the weight, so I'll put in 3 newtons. B was 0.08 newtons seconds squared per meter squared. I can now solve for V, and that's a special V, so we use the subscript T. I get 6.12 meters per second. Okay, all this looks well and good in theory. Maybe we can actually see it at home. Now you need to drop at home the rubber ball I gave you and the ping pong ball I gave you at the same time. You're not going to see much difference in 1 meter, maybe a little in 2, but after 3 meters, 4 meters, you're going to see the separation. Now you can set up a chair outside, put your phone on the chair, shoot it in slow motion, and go up to a window and drop it out like a 2nd-story window. Be careful, okay? As these two drop simultaneously, you'll be able to just get the bottom part and you'll see them separated in slow motion. Kind of hard to see the whole thing because as you get further back to get the whole shot, you won't be able to see the balls. Okay, so let's say you want to go big. Move the chair further away, get yourself a large colored ball so you can see it on the video, and measure this height from the window down to the ground. And when you do that, you can calculate the theoretical time for the ball to reach the ground. Do it experimentally. Play the video back, count the frames. That time is going to be longer than the theoretical. That's the air resistance effect. Okay, you want to review? All in print. Here it is. The next PDF on free fall. Got all the graphs in there, calculations, and then at the end, falling with air resistance. Here's a rock and a ball falling. Here's the different graphs. Here's the diagram, the free body diagrams. Here's the graphs including resistance. So have at it, folks. Good luck.